All right, good morning, guys. Today we're going to be getting started with this warm-up. So this is from 9.2, area of trapezoids. We want to find the area of the trapezoid. Now, to get started on this, I'm going to go ahead and find the area of this triangle over here. Because as we can see, we have a base and a height because they are perpendicular to each other. So the first thing I need to do here is I need to find the height of this triangle. If I find the height of this triangle, then I'll also have the height of the trapezoid itself. So in order to do that, I'm going to use Pythagorean's theorem. H squared plus 3 squared equals 5 squared. Now we may recognize right away that this is going to be a 3, 4, 5 Pythagorean triple. And if we do the math, we'll see that as well. 3 squared is 9, 5 squared is 25, 25 minus 9 is 16, and the square root of 16 is 4. So again, this is a 3, 4, 5 triangle, which means the height is 4. From here, I'm going to go ahead and bring that height over to our other side of our trapezoid. And I'm going to go ahead and draw the height over here as well. And what we'll notice when we draw the height is that it will create a 45, 45, 90 triangle. And of course, I can go ahead and draw a working 45, 45, 90 triangle because that is a special right triangle. Now, at this point, it's important for us to notice that this is not isosceles. And that's the most important part of this, because that's the most common mistake that occurs with this type of problem, is that oftentimes someone will look at this and they'll automatically assume that it is isosceles, but it's not. And the way that I can determine that is from our next step, because if I look over here, I see that x corresponds with the side length of 4. So if x is equal to 4, then I can go ahead and find out this part of my base as well, because that corresponds right over here with x, and again, x is 4, so this bottom portion is also 4 units in length. And of course, we'll notice that this 4 is not the same as the 3, further solidifying that this is not an isosceles trapezoid. Now, along with that, since in the middle here we have a rectangle, I know that opposite sides will be congruent. So the bottom portion of this must be 6 as well. So at this point, we have our height as 4, base 1 as 6, and base 2 as 13. Again, 13 is from 6 plus 4, which is 10, plus 3, which is 13. Plugging in our values into our area formula, area is equal to base 1 plus base 2 divided by 2 times height. Height is 4, half of 4 is 2. 6 plus 13 is 19. 2 times 19 is 38 units squared. Again, the most important thing that I want you guys to take from this is don't assume something is isosceles just because it looks that way. Make sure that you check through it first. All right, so today we are covering 9.6 area of segments, and we covered this in the past in Unit 8. I believe it was 8.11 as well. So this will be kind of a review section, and it should be fairly short for us as well. So the first thing that we're going to do is we're going to find the area of the sector. Now again, that's just the area of this section of the circle. And this is the same thing that we were doing in 9.5. So to find that sector, we just use area is equal to pi r squared times theta over 360. Now looking at this, we can see that our radius r is 13, and that theta is our central angle. It's 140 degrees. Now if it was this intercepted arc, that would also be theta as well. So plugging in our variables, we get area is equal to pi times 13 squared times 140 over 360. 140 over 360 can be reduced down to 7 over 18. And 13 squared is 169. So I have 169 pi times 7 over 18. 169 times 7 over 18, that will just give us 65.72. And then, of course, we still have the pi here. Multiplying this all out will give us our final answer of about 206.5 units squared. Now, if I want to find the area of a segment, again, that's just the shaded region here. So we notice that it's the area of a sector minus this triangle on the inside. Now, if we look at our formula, the first part of our formula is also the area of a sector of a circle. Again, that's this full segment that we just saw on the last problem. But the difference is I'm subtracting 1/2 r squared sine of theta. Now you may be wondering, where did this come from? Well, this is just the area of any triangle. And this comes from when we were dealing with the law of sines, law of cosines, and area of triangles back when we were doing right triangle trig. And that comes from the equation area is equal to 1/2 A times B sine of C. Now, again, with this equation, we would only use it when we had side, angle, side, which we see here. We have a side length and then an angle followed by a second side length. So that's the only time that we can use this equation. And whenever we're dealing with circles, specifically these segments of circles, that's all we're given. We're given side, angle, side. And you may be like, well, what are the sides? Well, our sides of this triangle are just radius lengths. And within a circle, we know that all radii are congruent. So therefore, it will always just be r times r. So both a and b here are r. That's where r squared comes from. Meanwhile, sine of theta, well, that's just the angle that's in between those two sides, which would be our central angle. So the theta that we use for our intercepted arc is the same theta that we use for our triangle as well. So in this case, we had 47 as our central angle, which is why theta was replaced with 47. So this is where we will be using this equation to find that segment. And again, it's going to be the same equation every single time. So let's go ahead and try some out. Again, 10 times 10, that's r squared, and 47 is theta. So our first one, we want to find the area of this segment. And again, that's just the shaded area here. And we notice that we have a few things. We have our radius as 3, and we have our intercepted arc's angle measure as 42 degrees. So using our equation, area is equal to pi r squared times theta over 360 minus 1/2 r squared sine of theta, we should be able to find out the area of this portion. Now, again, r is 3, theta is 42. Plugging in these values for these variables, we'll be left with area is equal to pi times 3 squared times 42 over 360 minus 1/2 3 squared sine of 42. From here, I'm just going to continue to simplify. 3 squared is 9. So I have 9 pi times 7 over 60 minus 1/2 9 sine of 42. Again, 6 goes into both 42 and 360. I'll go into 42 7 times. 6 will go into 360 60 times. 9 pi times 7 over 60 will give me 1.05 pi. And 4.5 sine of 42, well, that'll give me 3.011. Again, this is 4.5 times sine of 42. That's where this came from. From here, if I subtract 3.011 from 1.05 pi, we'll be left with our final answer as 0.288 units squared. Now, again, we want to check at the very end, does this make sense? Well, our angle measure is small, our radius is small, so therefore our area should be small as well. So yes, it makes sense in the context of this specific problem. Next up, we want to find the area of this segment. And in this picture, we can very clearly see that we had this full sector, and then I'm just taking out this triangle from it. So let's go ahead and use our area formula. Area is equal to pi r squared times theta over 360 minus 1/2 r squared sine of theta. In this case, radius r is 5. Theta is 120 degrees. Plugging in those values, we have 25 pi times 1/3 minus 12.5 times radical 3 over 2. And again, I just simplified it in my head. You can continue simplifying it as much as you'd like, or you can enter it into your calculator. 25 pi divided by 3 minus 12.5 sine of, or sorry, not sine, but radical 3 over 2. That's what sine of 120 is equal to. If we enter this into our calculator, we'll get our final answer as about 15.4 units squared. And again, just continue simplifying it until you feel comfortable entering it into your calculator. Next up, getting a little bit more difficult. We want to find the area of the segment, so this shaded area on both parts. Now, the first thing that we should notice here is that the chords WA and AT, they're congruent to each other. And if the chords are congruent, that means that the intersected arcs are congruent. So what that means is that these two segment areas will be congruent to each other. So I only need to find the area of one of those and then multiply it by 2. The first thing that I'm going to do is I'm going to find arc WT. Now, arc WT should be double the angle that is facing it. So, of course, I see angle watt is on the triangle, so it's an inscribed angle. So angle watt is going to be half of what arc WT would be. So if watt is 60 degrees, arc WT should be double that, or 120 degrees. Now, I also labeled arc WA and arc TA as X, because again, they're congruent to each other, so I should be able to solve for those arcs. The way that I can solve for them is that I have 120 plus X, and that will be equal to the full amount of degrees in a circle, 360 degrees. Solving for X here, I get 2X equals 240. And dividing both sides by 2, we get X is equal to 120. That means that this central angle I can say is 120 degrees, and again, our radius is still 10. From there, we can go ahead and plug in the values that we have into our equation. And again, I want to note that I'm multiplying it by 2 because I have 2 of the same area. This will give us area is equal to pi times 10 squared times 120 over 360 minus 1/2 10 squared sine of 120. Simplifying this down, this will give me 100 pi times 1/3 minus 50 times radical 3 over 2. If I divide 50 by 2, I'll be left with 25 rad 3. And multiplying 100 pi times 1/3 will give me 100 pi over 3. If I distribute the 2 through the parentheses, I'll be left with 200 pi over 3 minus 50 radical 3. Entering that into our calculator will give us our final answer as 122.8 units squared. That is the total area of both of these segments combined. Next up, we want to find the radius of the circle with an area of 33.093 inches and an arc measure of 95. So to get started on this, I'm going to go ahead and list everything that we have. We have theta and we have A, our area. Plugging in those values, we have 33.093 is equal to pi r squared times 95 over 360 minus 1/2 r squared sine of 95. Now at this point, I'm going to do a little bit of an algebra trick here. I notice that we have 2 separate terms, and again, terms are separated by plus or minus signs, and we have 1 minus sign in this equation. So I have 2 separate terms. Is there anything that both of those terms share? Or in other words, do they have a greatest common factor? Yes. The greatest common factor between these 2 terms is r squared. So I'm going to factor out an r squared, and that'll leave me with 33.093 is equal to r squared times 19 over 72 pi minus 1/2 sine of 95. Again, you can see that both r squareds were moved out, simplified the fraction, and that's all that we did there. If I enter in this entire thing that's inside the parentheses into my calculator, I'll be left with 33.093 is equal to r squared times 0.33093 repeating. It goes on forever. It's irrational. Now, the main thing that we should notice here is that the only difference between these 2 is if I move that decimal place 2 places to the right. So that's 2 significant figures. So if I want r squared by itself, I divide both sides by 0.33093, and that'll leave me with r squared equals 100. And that makes sense because, again, they're the same number if I move it over 2 places, which is 2 significant figures. So if I move that significant figure 2 places over, I get 100. From there, I can solve for r by taking the square root, giving us r is equal to 10. All right. Next up, we want to find the area of a segment whose circle has a circumference of 37.699 meters and an arc measure of 42 degrees. So to get started, we know circumference and we know our arc measure. We also know the formula for circumference. Circumference is equal to 2 pi r. So if I plug in circumference as 37.699, I should be able to solve for r here. If I divide both sides by 2 pi, I'm left with r is equal to 6. Now that we have r and we have theta, we can find our area. Area will be equal to pi times 6 squared times 42 over 360 minus 1/2 times r squared, which is 6 squared, times sine of theta, which is 42 degrees. Simplifying this down, 6 squared is 36. If I multiply that by 42 over 360, I'm left with 4.2 pi. Meanwhile, 6 squared is 36. Half of 36 is 18. If we enter this into our calculator, we're left with our final answer as our area being 1.15 meters squared. All right, guys, thank you so much for watching today. If you have any questions, please let